Differentiability refers to our ability to take the derivative of a function at a particular point. And if you remember how we first got to talking about the derivative, when we first started talking about the derivative, we defined it kind of as the slope of the line tangent to a curve at a point. And so implicit in the definition is that we're constructing all of this at a point, right? So you have the graph of a function doing whatever it's doing, you pick a point, and then we construct a tangent line there, and the derivative refers to the slope of the tangent line, right? The rise over the run. And you can only do this if the graph of f has a point there. So if the graph of f instead looked like this, we can't construct a tangent line at this place because there's no point there, right? So this tells me something. This tells me that we need a function has to be continuous at a point for us to even think about constructing a tangent line there, right? So the limit has to exist and the hole has to be filled in. Both of those things have to happen. For example, here we have the function defined at a point, but the limit doesn't exist there. Well, how are we going to construct a tangent line here? I mean, I guess we could, and it would be okay for the left part of this, but these tangent lines, they cut across the point, right? And so I don't know how you would do that here. So you can't construct a derivative here. You can't construct a derivative here. You have to have continuity to talk about the derivative. Okay, and to me, that makes a lot of sense and doesn't need a lot of proof, right? Is that all you have to have for differentiability? Well, almost. There's two little things that we have to look out for. So, points of non-differentiability, a vertical tangent. This does not happen too often. One of the places where it does happen the cube root of x has a graph that looks like this, kind of. It's got a vertical tangent line at x is equal to 0. Okay, so if the tangent line is vertical, what is its slope equal to? It's undefined, right? 0 slope looks like this. Slope of 1 looks like this. And then the steeper you make the line, the bigger the slope gets, right? 5 or something like that. And if it's straight up and down, it's infinitely big, and so we say it's undefined. Well, if the derivative is the slope, then if the slope is undefined, the derivative is too. So that's one thing that we need to look out for. Again, it doesn't happen that often. The other thing, which seems to happen a little more often, is what we call a cusp, and it's a pointy place on the graph of a function. So an example that we've seen a lot, I think, is absolute x. The graph of absolute x looks like this, and this is one of the functions that you worked with on the activity last week, where you were asked to graph the derivative of this thing. And I talked to a couple of you about this, but if you graph this correctly, the slope everywhere to the right of the y-axis is constant at 1, and the slope everywhere over here is equal to -1. So constant at 1 looks like this, and constant at -1 looks like this. And the sad truth is that at this pointy place, We don't know how to define the derivative there, right? Because if you're coming in from this way, it's -1. If you come in from this way, it's +1. What do you do when you get there? I don't know. Take the average? No. We just said no. The derivative doesn't exist there. So on the graph of the derivative of absolute x, we have open holes there where x is equal to 0. So a more general case might be something that looked like this. So if you had some weird kind of function that looked like this, the derivative would exist everywhere except at this point. Notice that the function is at all of these places. It's not a point of discontinuity, is it? No, I can draw this without any trouble at all. I don't have to lift my pen. So it's continuous here, and it's continuous here, and the graph is continuous here. But the derivative does not exist because of the way we have defined it. So that's what I have to say about limits, continuity, and differentiability.